Hello everyone, this is Uday and welcome to Uday Lectures. In this video, we will discuss about binary search tree. So without any further delay, let us get started. A binary search tree is an ordered binary tree, and we can also call this as a sorted binary tree. Why we name this binary search tree as an ordered binary tree or a sorted binary tree is because the elements in binary search tree or nodes in binary search tree are arranged in an order, and we follow a specific order in inserting values into the binary search tree, and because of this reason we say that this particular binary search tree is an ordered binary tree where we follow a respective order to store the given values in the binary search tree. And it is developed independently by many researchers, and it is a contribution of many researchers where the binary search tree is developed. And in binary search tree, any given node, it contains all the smaller values in left subtree. And if you take the right subtree of binary search tree, it will have all the bigger values for any given node. Let us look into the binary search tree and try and understand why it is an ordered binary tree. So here you can see that there is a binary search tree, and here you can see all the left subtree elements are smaller than the given node. For example, if you take this root node, which is 19, all these particular values in left subtree are smaller than this particular root node. And you can also see this right subtree where all the values, which is 20 and 30, are bigger than the given root node. So this rule is not only applied for root node, it can be any given internal node. For example, if you see 10 in this particular subtree, or for 10, the left subtree values, which is 5, is the smaller element compared to 10. And if you take 15, it is a bigger value compared to 10. And if you take this subtree, we have 20 as internal node, and here 30 is the child of 20, where 30 is bigger than 20, and that is why it is inserted to the right side of 20. And this is how a typical binary search tree would look like. Now we try and understand the properties of binary search tree. So the properties of binary search tree goes like this, and this can also be called as rules of binary search tree, which has to be satisfied by any given binary search tree. So the very first rule is that all the smaller elements must be in left subtree for any given node, and all the bigger values must be in right subtree of any given node. And not only that, any node in the binary search tree can have only one value, which we can also say as one key. And no duplicate nodes must be in binary search tree, and duplicate values are strictly ignored in binary search tree. And here there should not be more than 2 child nodes for any given tree, for any given node in the binary search tree, and this rule must be satisfied. And not only this rule, all these particular rules must be satisfied to say that a given binary search tree is a valid binary search tree. Now let us look into an example and understand what these properties are. So here I have given you an example, and this example binary tree, we say that it is a valid binary search tree, and the reasons are this. So you can see that none of the nodes are having more than 2 child nodes, which is satisfying this property. And also you can see that all the values are unique in the binary search tree, and there are no any duplicate values, and any given node is having only one value or one key. None of the nodes are having more than one key value in the given node, or any node it can be. And this particular rule, which states that all the bigger values must be in the right subtree. If you take 20 and 30 are bigger than 19, so they are in the right subtree, and 30 is bigger than 20, so it is in the right subtree of 20. And likewise, you can also look into the left subtree where it is satisfying all the rules, that all the smaller elements are in the left subtree. For example, 10, 5 and 15 are smaller than 19, so they are in the left subtree of 19, which is satisfying this rule also. Since it is satisfying all the properties of binary search tree, so we say that this binary search tree is a valid binary search tree. Now let us understand an invalid binary search tree, how it would look like. So here I can say that this binary search tree is an invalid binary search tree. The reasons are this. If you take this root node or this node, there are more than 2 child nodes, which is 10, 20 and 2. Since this is having more than 2 child nodes, it is violating this rule. and we go ahead and say this particular binary search tree is invalid. Not only this property, and the other properties are also being violated. So this property says that no duplicate nodes are allowed in binary search tree. Here if you see, there are 30 twice, and also there are 2 twice. Since there are duplicate nodes in this binary search tree, we say that this binary search tree is invalid. And not only that, even this particular property is being violated. Bigger values must be in right subtree. But if you look at it, so there are elements like 2, which is smaller than 19, but still it is inserted to the left side of 19. So we say that this binary search tree is invalid. Not only there, even here it is being violated. So 2 is smaller than 10, but still it is inserted in the right subtree of 10. So which is violating the properties of binary search tree. Since it is violating the properties of binary search tree, we say that this binary search tree is invalid. So it is not that all the properties must be not satisfied to say that it is invalid binary search tree. It can be any of these properties. So even one of the property is not satisfied, then we say that that binary search tree is invalid. Now we will see what different operations we can perform on binary search tree. So we can perform insertion operation, and also we can perform search operation on the given binary search tree, and we can also perform deletion operation. So here I'm asking to insert 5. So into this binary search tree, I can go ahead and insert that 5 at this particular position. Do not worry. So I will make a specific video for binary search tree insertion, and in next video we will see how insertion operation happens in binary search tree with example. And I'm asking to perform search operation. If you'd like to find whether a particular value is present in this particular tree or not, we can use search operation to perform it. So the outcome of this particular operation will be 20 is available. So since 20 is already in the binary search tree at this particular position, we say that 20 is available in the binary search tree. And not only that, if you would like to delete any nodes from this binary search tree, you can go ahead and delete it. And the deletion operation works only if that particular element is available in the binary search tree. And since in this case I'm asking to delete 15, I can go ahead and delete this 15 by following a particular procedure. And do not worry, in next video we will be looking and we will be discussing about insertion operation, search operation and deletion operation with specific examples, and you will be able to understand them very clearly. Now we will see the complexities of binary search tree, which is really important for any data structure. So the time complexity and space complexity of binary search tree goes like this. The time complexity of binary search trees are like this. So in worst case scenario, the time complexity will be big O of n, which is equivalent to the size of the binary search tree. And in average case, the complexity is big O of log n, which is height of the binary search tree, and it is equivalent to the big O of log n. And in best case, it is in constant time, which is big O of n, big O of 1. So do not worry, we will try and understand these complexities with an example. And let me consider this example to make you all understand this time complexities in different scenarios. So for example, in best case scenario, if someone is asking you to search 19 in this particular binary search tree, you can go ahead and perform this operation. So here 19 is present in the root node position. The number of comparisons that I'm going to perform is only 1. So here you can see that the number of comparisons, since 19 is equals to 19, I can go ahead and say that 19 is available in this binary search tree. And the number of comparisons that we have taken is only 1. So we can go ahead and say that the best case complexity, the time complexity or the time taken in best case scenario is big O of 1. And in average case, it is big O of log n. Let me explain that with an example for you. So if I am asking you to search 30, right? I'm asking you to search 30. Now let us make comparisons. So the searching element is 30 and the root node element is 19. So if you make comparisons, 30 is bigger than 19. So you have to go make further search operations in the right subtree, but not in the left subtree of binary search tree. So the next element in the left subtree or right subtree of this binary search tree is 20. Again we make comparison, and again 30 is greater than 20. You have to again go to the right subtree of this particular node. And here you can see that 30 is equal to 30. So we can go ahead and say that 30 is available in the binary search tree. But what about the number of comparisons? So how many comparisons did we take here? We have taken 1, 2 and 3. So the number of comparisons that we have taken is 3. But if you look very closely, so the levels are also 3 in this binary search tree. So the number of levels in this binary search tree is 3, which is also equal to the number of comparisons that we make. So the height of this binary search tree can be defined like this, which is log n. Alright, so where n is the number of levels. So here the number of levels are 3. So the number of comparisons that we did take is 3. So the height of this binary search tree is log n. So in average case scenario, the time complexity can be said as big O of log n. And that is why in average case, time complexity for binary search tree is big O of log n. Now let us understand in worst case scenario what is the time complexity. Let me take this example. So the worst case scenarios happens in binary search tree only if that tree is a skewed binary tree or a semi-skewed binary tree. Alright, so here I can see that this binary tree is completely right skewed. That means all the values in this binary search tree are in the right subtree of the complete tree. So here if I am asking you to search an element, let me say I would like to search 40, which is an example for the worst case scenario. Now let us make comparisons to understand this. So since 40 is greater than 19, we should go make comparisons in the right subtree of 19. So the right child of 19 is 20. And again make comparison. And again 40 is greater than 20. So again we go to the right child of 20. And right child of 20 is 30. So make comparison again. And 40 is greater than 30. Again we go to the left side or sorry, right side. And again we make comparison. So here 40 is equal to 40. Then we can go ahead and say that the 40, the element which you would like to search, is available in the binary search tree. But what about the number of comparisons that we take? The number of comparisons that we take is 4. So here the number of comparisons are 4. And if you also look closely, the number of nodes that there are in this binary search tree is 4, which is equal to the number of comparisons. So if you take there are n nodes in the given binary search tree, and in worst case scenario, you will end up with a time complexity of big O of n, because the number of comparisons are equal to the number of nodes in the binary search tree. And this is why in worst case scenario, the time complexity is big O of n. And coming to the space complexity, the complexity is big O of n. So why we tell that space complexity is big O of n? Because the memory has to be accumulated for all the given values in the binary search tree. For example, in this binary search tree, there are 4 nodes or 4 values. So the number of memory locations that are required to store these values are 4. And that is why the space complexity for binary search tree is big O of n. Hope you have understood the complexities of binary search tree also. And with this video, I believe you have understood the introductory part of binary search tree and the complexities of binary search tree, which is really important. And if you like the content of this video, please do subscribe to this channel to watch further videos in my channel. And if you like this video, please do give a like and also share this video with your friends if you feel this content is really helpful for you in understanding this topic very clearly and very easily. And in next video, we will look and we will discuss about the insertion operation in binary search tree. And in later videos, we will discuss about search operation and deletion operations with an example. And thank you so much. Have a wonderful day ahead. Thank you.